This playlist collects together videos covering the probability problems section of our test. We'll start off by looking at estimating the probabilities for simple events. Our probability theory is going to work to help us calculate the probability of complex events from simple events. So whenever we have a event that we want to calculate the probability for, we're going to first have to break it down to see what kind of event it is. And if it's a complex event, we want to break it down to those simple events. Once we get to the simple events, we want to assign probabilities to each of those simple events and then use our 5 rules to calculate the probability of the complex event from the probability of the simple events. So we'll start off assigning probabilities to simple events. And the way we've been doing this in the context of the lectures is by looking at the different interpretations of probability theory and noting that each interpretation has a particular set of problems that it straightforwardly helps you to assign a likelihood to. So we'll start off by looking at the different interpretations of probability and how we can use them to assign probabilities to simple events. So our probability is just expressed as the ratio of favorable or target outcomes, the things that would make our event true, divided by the total number of possible outcomes. Those values are going to range from 0, which is impossible, to 1, which is inevitable or certain. And the ratio will always be favorable divided by the total number of possible. So let's start with the classical conception of probability theory. So the classical conception of probability theory applies because we know all the possible outcomes. That is, we know everything in n, that denominator. We know every different possible way the world could be. And importantly, we also know the following. We have reason to suppose that the principle of indifference holds. And the principle of indifference just says that each possible outcome is just as likely as every other possible outcome, so that no possible outcome is favored. Nature is indifferent towards the different outcomes. So if we know all the outcomes and we have good reason to suppose that none of them is more likely than another, we can always use the classical conception of probability to assign probabilities to the simple events. So let's take an example. What are the odds of rolling a 3 on a single roll of a fair die? So the first thing we'll know is that we know all the possible outcomes of our roll of a die. That die has 6 faces, and so there are 6 possible outcomes. And so our n is going to equal 6. Because it's a fair die, we know that every side is just as likely as every other side to come up upward facing on any given roll. And so the principle of indifference holds. And so we can assign the probability of rolling a 3 on a single roll of a fair die using our classical conception and plugging in those numbers. So the probability of rolling a 3 equals the favorable or target outcomes divided by the total number of possible outcomes, which in this case is going to equal 1, the number of faces that have 3 dots, divided by 6, the number of possible outcomes or different faces on our die. The next interpretation that we're going to look at is the frequency interpretation. Now, the frequency interpretation holds that the probability of an event is the number of observed favorable outcomes divided by the total number of observed outcomes as that total number goes towards infinity. That is, as you get more and more and more and more observations, that ratio of favorable to total number of observations will come closer and closer to the actual probability number. So in this sense, we never really know the frequency interpretation probability for an event. But we can estimate the probability for an event under the frequency interpretation by taking the observations that we actually do have. And so we estimate the probability under the frequency interpretation by assigning the probability to an event as being our observed favorable outcomes divided by our total number of observations. When do we want to use the frequency interpretation? Well, the frequency interpretation suggests itself when the outcomes are somewhat less than determinate. So we may not know all the different possible outcomes in the world. We have no reason to suppose that the principle of indifference holds. This is particularly important. So we may know a number of different possible outcomes, but we have no reason to suppose that they're equal in number. And finally, we have some observations which we can use to base an estimate of the probability using the frequency interpretation. So here's an example. Suppose over the last year, your colleague has been late to the office 4 times. So our outcomes are somewhat less than determined. Right? The person could not come in because it's a holiday, it's a weekend, the company's gone bankrupt, and so on. So there are a bunch of different possibilities out there. All right. We have no reason to suppose that the principle of indifference holds because it's not a 50-50 chance that your colleague has come in or not come in. And we do have a set of observations that we can use to estimate our probability. So then we can come up with an estimate for the probability that your colleague will come in late by taking our favorable or target observations, those 4 times the colleague didn't come in on time, and divide that by the total number of observations that we've made. So in a given year, assuming you have 2 weeks off and a few holidays, you got about 247 work days. So 4 divided by 247. Finally, we have the Bayesian interpretation. Now, the Bayesian interpretation represents your best estimate of the likelihood of an event, and it's usually quantified as the probability being expressed as the odds that you would accept as a fair bet. So when are we going to use the Bayesian interpretation? Well, if it's a unique event so that we can't use frequencies, if the number or kind of outcomes are indeterminate so that we're limited in our knowledge about the outcomes, or if we have very little or poor quality of information about the relative frequencies. We don't have any reason to suppose that the principle of indifference holds. In these cases, we'll probably use the Bayesian interpretation. So for example, if you're trying to estimate the probability or the odds of the Lakers beating the Bulls on Thursday, that's a unique event. There are a number of different possible outcomes. They could tie, they could win, they could lose, the game could be canceled, and so on. And we don't have a lot of good quality information about what's going to go on during that game. So it's probably a good candidate for a Bayesian estimate. So we would then say, well, how many times do we think they'd win versus how many times do we think they'd lose? And that's how we'll calculate the probability. So if we say, I'll give you 6 to 8 odds, all right, then we're saying 6 times we think that they'll win and 14 times they'll play. So 6 over 14. So 6 plus 8 plus 6, 14.